Good morning, everybody. Welcome back to another session of data science training from 360DigiTMG. And the topic that we were discussing in the last class was about the time series data, and we have spent quite a bit of time in time series data. So we discussed about time series and cross section. We discussed about data. We've also understood, thanks to the example, about the additive and multiplicative. Now, all these things are making more sense given that we have progressed further. When you look back, it is making more sense. All right. And what is level, what is trend, what is seasonality, and of course, noise. There's really nothing much one can do with noise. All right. That is one of the big disadvantages. And then the time plot, the lag plot, and then finally the ACF plot. The applications of ACF plot, how to look into it, all these things is something that we learned. All right. And can you please tell me if you have done the study of rule of parsimony and the Occam's razor? How many of you have managed to do that? Rule of parsimony and the Occam's razor. Could you get time to do a study on that? Okay. Apparently, nobody has made any serious study about about the Occam's razor, right? I thought maybe something that would be interesting. So there you go. We have the explanation given by Mallikarjun Rao. All right. Good. Okay. So then we discussed about the EDA, the importance of EDA. The importance of EDA was explained by virtue of, actually ignoring the EDA, right? When we did the experiment, we actually ignored the EDA, and because of that, we learned the importance of EDA. All right, that was something interesting. And then we discussed about the partitioning. All right, it has to be in series. We shouldn't jumble the data. Naive forecast, the concept of error became even more clear once when we found out that error actually contains information, and that information must be used to improve the forecast. We also realized that we cannot really get the actual future value, but we can improve the forecast by forecasting the errors as well. And when you have errors, you're going to have a measure of error which is most popularly used, which is RMSE. All right, we've seen multiple models across RMSE, and then we talked about two of the models, linear regression models and then AR models. All right, so that is what we had done till the last class. All right, and there's another thing which is called as random walk. All right, random walk essentially says that if your data is having random walk, then it is difficult to predict. All right, now, or difficult to forecast. Now, to understand about that, all right, if you build an AR model, and if the beta 1 or the coefficient value is 1 or close to 1, then your model is having random walk. Now, what does the beta 1 is equal to 1 imply? Can you tell me what does beta 1 is equal to 1 imply? In the AR model, when beta 1 is equal to 1, what does it imply? It implies that there is a very good correlation between the original and the lag. Is it making sense? If the beta 1 value is 1, then there is a very good correlation between the original and the lagged value. The lagged value could be lag 1, lag 2, whatever, which means there is a very good correlation. If there is a very good correlation, then it automatically implies that now when do you have very good correlation? You have something like this, which means this leads to that, that leads to this leads to that, that leads to this. All right. If there is a very good correlation, what does it tell you? It tells you that the data is essentially the same. You have taken the lag one, but still you are getting a good correlation. All right. So what does it mean? If I have, when will you get good correlation? Let us say I have 3, 3, 3, 3, 3, 3, 3. The lag one of this would be 3, 3, 3, 3, 3, 3, 3, 3. The correlation between this will be 1. Now, is this really any data? All right, is this really any forecasting value? Forecasting data, it is all the same. All right, so therefore, it is just moving randomly. It is moving up, 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 or going down, down, down. It is, there's no cyclicity, there's no up and down. Only if there is an up and down or some cyclicity, you would have an correlation which would be lesser. All right, you will have a correlation which would be lesser. Are we good? All right. So, okay, this is just the case step thing. So now let us move on to the next approach of forecasting, and that is the data-driven approaches. All right. Now, what is data-driven approaches? It is simply the scenario when. Okay, let me just try to explain about the relationship or the thing between model-driven and data-driven first, the difference between them, and then you will move into that. Okay. Now, the model-driven approach tries to imitate exactly the way things are moving. It tries to kind of imitate it, all right, exactly the way things are going, and therefore this is how the forecast will be. So the model-driven approach is, if it is good, it is very good. If it is bad, then it is very bad. Now let me explain to you what do I mean by if it is good, it is very good, and if it is bad, it is very bad. Okay. Now, for instance, if my data were originally something like this, something like this. Now, when I take the training data, my model tries to imitate this. It will not be fully able to imitate. All right. I cannot have a same model go through the entire thing. Let me just delete that thing into a different color, probably then it will make sense. So this is my data. And when I try to take a model, the model tries to approximate between this, ultimately regression. All right. And then when the forecast happens, you see how far away the forecast is. Are you able to see the errors of the forecast? The point I'm trying to make is if the data is good, if it is systematically without any hassles, quietly, calmly going up, then your model driven approach is amazing. But if the data is something that they say in this thing tends to have a very high volatility, or data tends to have a lot of erraticity. It'll be erratic, it'll suddenly come down, this thing. All right. Now these things would be because of market conditions or things like that. Now, developing economies, all right, India, um, Afghanistan, Bangladesh, all right, you would expect any economic policies, anything will happen, you'll have something like this. US currently, what is happening, that would be probably like that. Now, when you look at the European countries, all right, except of course for UK because of Brexit, generally when you look at Germany or any of the other countries, it is pretty stagnant. All right, anything you do, if the government changes, nothing happens. If the government is not there, nothing happens. All right, that is how stable the things are. So in developed economies, you expect the data to be pretty much consistent and have very little or no volatility. All right, you may make a note of this and we may want to Google it, volatility. All right, now what about the data driven approach? This is the data driven approach. So when I have data, this is my data, I'm on purpose giving it a very high trend now. So if excuse me, if this is my data, it averages between it. Not a very good one. Let me just try it again. Maybe I'll use this. All right, I put a line through it, an approximation line through it. Now this approximation line, as it is not all that great. Now compare it to the model driven approach where you have, again, I think I'll use the same color code because it makes things easier. So data is in green color. So let me also put the data in green color. So in the model driven approaches, if your data is like this, and if you look at the model on the model driven approach, it is going to be all right, it is going to be like that. Now, for the same data, I once tried the data driven approach and I tried the model driven approach. Obviously, the error associated with the model driven approach is going to be much less compared to the data driven approach. So data driven approach is not good. As it is not good, but it does not become very bad. Do you understand? Quick confirmation if you've understood why model driven. Yeah, quick confirmation if you understand why model driven approaches is very good, but if it is bad, it is very bad. Whereas data driven approach is not all that great, but never becomes very bad. Is it making sense? So data driven approach is an approximation. All right, that is why it is called as smoothing. All right, it is a smoothing method. Okay, so what is the assumption when you are dealing with model driven approaches? Past is similar to the future, or more appropriately, I think past is similar to the future is a wrong statement. It should be we expect the future to be similar to the past. I think that is more appropriate, right? We expect the future values also to be similar to the past. What is the data-based approaches? Past is not similar to the future, or future will not be similar to the past, whichever way you want to look at it. If you get the idea, that is what it is. All right. So now let us go ahead and learn about the smoothing methods. One of the easiest smoothing method is a moving average. All right, is the moving average, which is you add up these things and then divide it by k. So success depends on choosing the window width k. How many values are you choosing to do the smoothing? And you have to do a balance between over smoothing and under smoothing. Now, what is over smoothing? What is under smoothing? Isn't it something similar that we have learned? What is over smoothing? Similar to over smoothing. 1 minute, please. Yeah. Similar to over smoothing, you have learned something else. Yeah. All right. Over smoothing is not overfitting. Right? Over smoothing is not overfitting. Remember that. Over smoothing means I am taking into consideration too many of the past values for my prediction. All right. Too many of my past values I'm taking into consideration for my prediction. What is the meaning of that? If I have to choose a window width that is very, very large, all right, a window width that is very, very large, then I'm unnecessarily taking into consideration the other values also. Okay. We will discuss a little more about over smoothing and under smoothing in a moment. All right. Now we also have something what is called as the exponential smoothing. All right. The exponential smoothing, we have alpha yt plus 1 minus alpha yt hat. Now what is this yt hat? What is this values? All these things we will learn very soon. All right. Now let us first discuss about the moving average. All right. So what happens in the smoothing or the moving average work is that it smoothens out the noise also. Okay. And it is good for data visualization. Obviously, it is good for forecasting, and it helps in removing seasonality and also computing seasonal indexes. Now, why do you want to remove seasonality? What is seasonal indexes? All these things we'll learn. All right. All these things we'll learn. And let us first understand about the moving average calculation. Okay. So centered, there are two methods or two ways of doing the moving average. One is what is known as the centered moving average, and it is calculated based on the window centered around time t. Now suppose I want to keep the window width as 7. All right, window width as 7. Then I can take values before, after, and in the middle. Now, if you look at this, sorry. One, 2, 3, 4, 5, 6, middle value. Or more appropriately, if you want to give it a different spin to it, 1, 2, 3, 1, 1, 2, 3. Is it making sense? Is it making sense? All right. Now, in the case of trailing moving average, we are taking the value that for which we want to find the moving average, and we are putting it in the back. So the window width is again 7. Now this square has not come out very properly. So ideally, what is the value? We have 1, 2, 3, 4, 5, 6, 7. This should have been something like this. That would have been slightly better. Is it clear? So I'm taking a trailing value of that. All right. Now, if you have to do the trailing moving average, let us say window width is equal to 4 or 5 or whatever. Let us say window width is equal to 5. Then this is what it is. All right. So if let us say window width is equal to 5, then you have here 5, 5, etc. So what is this? Y t minus 4, y t minus 3, y t minus 2, y t minus 1, y t divided by 5, because 5 minus 5 plus 1 is 4. All right. This is of course the case of the trailing moving average. Now what if we have to do the centered moving average? Now in the centered moving average, if your window width is an odd window, then no problem. Is it making sense? Are we good here? Are we good here? All right. Now when you want to take an odd width, let us say the window width is 4, then we'll have a problem. So what we are going to do is we are going to take something called as the almost centered. So when I take the window width is equal to 4, all right, so what it means is, one moment. So this is where the center value is. Is it making sense? The center value will be between t minus 1 and t. Now, when you take we take another window width, which is like this, and for this, we have this, and for this, the average value will be here between t and t plus 1. Now, if I were to take the average of the green and the red arrow marks, what will I get? I will get this arrow mark. Is it clear, friends? So what we'll do is we'll quickly do a hands-on. All right, we'll quickly do a hands-on. We'll do it in Excel itself. It's very easy. Let me just open that file. Yeah, we'll do a hands-on. Just give me a moment while I open the file. All right, we have the data here, and we should definitely always do what when we get the data? We should definitely always do what when we get the data? Absolutely right. Absolutely right. Only yesterday we learnt about it, right? The importance of EDA. We had not done the EDA properly. That is why we ended up doing all those models, visualization, EDA. So let us do the EDA. All right. Now, once again, if you want to understand about this data, take it for one complete seasonality. So we see that it is quarterly data. So 1 year, 2 years. All right. And if you want to, figure it out even more, probably or better still, is it clear? All right. So at least the quarter one draw to draw relationship is pretty much there. This peak, it should have been like this, but it became like this. So there is a noise component to this. All right. There is a noise component to this. Is it clear, friends? Okay. So anyway, this is the data. Now for this data, we are planning to do the centered moving average. Now, we have the quarterly data. So a good idea is to do the quarterly when you have, let us say, data with seasonality. A good idea is to divide the or do the moving average with the window width of one complete seasonality, and therefore one complete seasonality is equal to 4. All right. Now let me start with Q3. All right. Let me start with Q3. And here we have two values of the past, one value of the present, one value of the future, plus one value of the past, one value of the present, two values of the future, divided by 2. Is this formula clear? Are you able to understand? Is it making sense, friends? All right. Now, why didn't I put this formula here also? The reason being, this would refer to a blank entity. All right. This would refer to a blank entity. Therefore, we don't go above. All right. Similarly, I am not going further down here because this is again referring to a blank entity. Are we clear, friends? Now you have, this is the moving average. Are you able to understand the averaging method? Is this making sense? All right, this is the moving average. Now, next we are going to be discussing about what is known as the exponential smoothing. All right. So as part of exponential smoothing, there are multiple methods. We have simple exponential smoothing, we have Holt's method, we have Winter's method. All right. Simple exponential smoothing assumes that there is no trend and seasonality and there is only level in the data. And therefore, it smoothens the level component. All right. It smoothens the level component. The Holt's method assumes that there is trend but no seasonality, and therefore it will smoothen the level and the trend component. And Winter's method, also called as Holt's-Winter's method, all the three are there, and therefore we will get smoothing for the level, trend and seasonality. All right. Now let us look at this. The formula for the exponential smoothing, simple exponential smoothing, is the future value with a smoothing constant alpha with yt plus 1 minus alpha into the forecasted immediate past value. All right. So let me just write this down. Okay, yt plus 1 hat is equal to alpha yt plus 1 minus alpha yt hat. All right, 1 minus alpha yt hat. Now, if this formula is there, then what is yt hat? By the same logic, then what is yt minus 1 hat? Are we clear, friends? Is it making sense? Maybe I'll just write down one more step. What is yt minus 2 hat is equal to alpha so on and so forth. Now, let me substitute the yt value here, yt hat value here. So what happens is my formula becomes now yt hat is this part of the formula, which is now yt minus 1 is this part of the formula. Now, do you understand why I'm going on writing brackets in the end? Is it making sense? So let me solve this. So what I get? All right, alpha into 1 minus alpha. 1 minus alpha into 1 minus alpha into alpha. One minus alpha into 1 minus alpha into 1 minus alpha into 1 minus alpha into 1 minus alpha into alpha. Is it clear? Right? There was a reason why I have taken so much pains to, write this down. All right. Now, when you come here, we are going to, the whole essence of this entire smoothing is to be assigning an alpha value, which is the smoothing constant, which should be in the range of 0 to 1. All right. Now, if the smoothing constant is very, very small, now I cannot have the smoothing constant 0, because if I have smoothing constant 0, then what is going to happen? Everything collapses. I don't want that to happen. Let us say I have a smoothing constant close to 0, 0.0000000001. So the importance of this value is greatly reduced. Now, what is 1 minus alpha? If alpha is 0.00000001, 1 minus alpha is a value close to 1, 0.99999999. And what is 0.999999 into 0.00000001? It is nothing but 0.00001 into 1, which is again combined a very small value. 0.999 into 0.999 is equal to 0.999. So once again, so what I have done is I have effectively reduced the importance of all, but kept all of them at the same level. Do you understand? By keeping the alpha value very small, I have effectively reduced the importance of all, right, and kept the importance for all the coefficients, all the values, the immediate past and the very old, all of them are giving equal importance. This phenomena is called, let me just skip a few slides. This phenomena is called over smoothing when alpha is equal to 0. Is it clear? No, alpha is not equal to 0. If you notice this formula, close to 0. Now, what if happens if alpha is equal to 1? What happens if alpha is equal to 1? So only alpha yt is left, which means what does this become ultimately? It becomes a naive forecast, a last sample method. And if you have a value very close to 1.9999999999, same thing. If you have the value 0.9999 also, this is at 0.99999 approximately is equal to 1. So this becomes yt. And all these values are equally pulled down, because here you have 0.00000001 into this is going to be 0.001. So all these values are pulled down. Still, this is the best value, and these values are near 0 values. Again, it doesn't help. So you have to be very judicious in the choice of the alpha. Thankfully, we don't have to bother about it. Most of the people, the mathematicians and the statisticians and the forecasters, all right, have already told that the good value for alpha is 0.1 and 0.2. Is it clear? All right. So this is what the explanation in the next slide is, what I've already explained. All right. And this formula, ultimately what is being tried to explain here is that simple exponential smoothing assumes that there is only level. And therefore, when you're talking about level, all right, when you're talking about level, then you only talk about the L. All right. And that is what is basically being done here. All right. Okay. We will come back to all these things in a moment. Then we have something called as the double exponential smoothing, or also called as the Halt's method. Okay. The double exponential smoothing assumes that there is level and trend. So therefore, you're going to get a smoothing constant for level as well as trend. So you have a smoothing constant for level, which is alpha. For trend, it is beta. And on similar logic, you extend the same understanding. All right. You extend the same understanding. That is what happens. Okay. So thankfully, again, the statisticians have told that 0.1, 0.2 is good for alpha. Something around 0.2, 0.15 is good for beta. And then if you have the Winters method, which is you have the level, trend and seasonality, then you have the alpha, beta, gamma. Each one smoothens each of its components. All right. And you have the values. The gamma value is generally kept at a very small value, 0.05, but then we have cases wherein we have used a much higher gamma value as well. So are you clear about these three methods now? All good? Okay. Yeah, sorry, just for something else. So let us now do the hands-on. All right. Let us now do the hands-on for the smoothing techniques. Let me open the file in one moment. Yeah, so here we go. We have the entire code ready with us. The code looks pretty big, but is not all that big. Don't worry. Yeah. Okay. I don't know why this keeps coming. Let me just erase this. So we have loaded the package called forecast. Okay. And then there is a package called FPP, forecasting principles and practices. All right. That is one thing. Then we have something called as T series, not to be confused with the music company. It is the time series. All right. T series stands for time series. It is already loaded. All right. And we have to have the read Excel because we may be loading some Excel files. Perfect. So now we are going to be loading the Coca-Cola sales data. All right, Coca-Cola sales data. Why is it not coming? All right, we are loading the Coca-Cola sales data. And if you view the Coca-Cola sales data, yeah, we have a friend Buddha Sai Dinesh who's having some difficulty. He's trying to adjust his phone and repeatedly turning on the webcam. Yes, Sai Dinesh, B Sai Dinesh, your webcam is on. You want to keep continuing your webcam or you want to close it? I don't think he's listening to me. I think he's Sai Dinesh. Buddha Sai Dinesh. Okay, let me see if I can close it at my end. As a matter of fact, I can. Okay. Didn't realize that. All right. So this is the data we have, quarterly data of Coca-Cola sales. This is 42 observations and 2 variables is what we have here. All right. Now, this particular data, we are going to be converting it into a time series data. All right. So what is time series? All right. Time series object. A function TS is used to create time series objects as.ts or is.ts to coerce and test whether it is time series. So you can probably go through all the details, blah, blah, blah. So what I'm going to do is I'm going to define Coca-Cola sales within that the sales column as time series with frequency is equal to 4. All right. And you have your time series data. All right. Now that it has become a time series data, it will be easy to do the other applications also. All right. Okay. So I think it's time for a break. I have some urgent work, so I'll probably take a little longer break. So excuse me, very sorry. Yeah, a little longer break today, friends. I hope you understand. Friends, it is taking a little longer. I'm in the middle of something. Team, can you please give the attendance so that they can post it? Yeah. You can post your attendance while I'm just back. Very sorry. Very sorry for the delay, friends. Some engagement. All right. Let's continue. So we have converted the data into time series. Now, if you look at TS sales, you only have that particular column. All right. You only have that particular column which has the time series data. All right. And we have mentioned the frequency as 4 because we know the seasonality is 4. Okay. Now we are going to split this particular time series data into train and test, and one complete seasonality is 4 values. So therefore we are going to take 38 and 4. Now the problem with this splitting is that once you split the TS data into train and test, it loses the time series aspect of it. All right, it's no longer time series. So what we do, we convert them again into time series. So whatever is train, I reassign it to train with the frequency 4 as time series, and similarly with test. So now I have the entire data in time series, the train data in time series, and the test data in time series. All right. Now we can plot the entire data TS sales, and this is what it looks like. All right. Then this is for the purpose of visualization. Now we are going to do the simple moving average. So simple moving average command is pretty straightforward, just SMA. All right. So when I run SMA, simple moving average, could not find SMA function. Let me just check. Forecast is there. Smooth has not been. Smooth is the func variables thing that I have not let loaded. That is why it is creating a problem. All right. Now that SMA is a, obviously simple moving average is a smoothing method, and that is part of the smoothing package. So now when I go up and now if you want to do this thing, no, now I could make out that it is smoothing with my experience, but what if you have a problem like this? A particular function is not found. So you can simply, I don't know if I've already told you this, but I'm just telling it again. Just pick this up. All right. And do this. SMA simple moving average. All right. Require smooth. Require mcomp. These are the two things that may be required for that. All right. So you can figure it out. And you also know what is the difference between require and library. So now coming back here, when I do the simple moving average, done. And if you want to know what SMA is, simple moving average, you can probably read it at a later point of time. Then using this MA model 1, I'm going to predict horizon is equal to 4. All right. And whatever I'm going to predict, I'm going to put it into a data frame and put it into MA underscore pred. So when I do this, I have MA underscore pred. And if you look at this, 95% confidence, minimum and maximum, and these are the values. All right. Now, if you want, we can also plot this particular model. All right. So MA model 1, if you plot it, it's because of it being a time series, we are able to do that. All right. So this is how the smoothing goes till here, it imitates, and then for the remaining, it goes like this. All right. It extrapolates like this. All right. And also we have the intervals. Okay. So this is moving average. All right. Now This here is the computation of what is known as the MAP. MA.pred, the value, $point forecast, compare it with the test. So this is one value y hat, and this is the other value y. Between these two, find the MAP value. So the MAP value gives it in percentage terms. All right, gives it in percentage terms, and we are putting it into 100 so that we get it in 8.9%. All right. Is it clear? Okay. Next, let us use the halt winter method. What about simple exponential smoothing? We will do simple exponential smoothing also using halt winter method. Now remember ARIMA, AR, I, MA. All right. So what we did, for the AR we gave a value, for I we didn't, for MA we didn't, and therefore we got, while the command was ARIMA, it essentially became a AR1 model. Similarly, I am going to give the alpha value is equal to 0.2, beta false, gamma false means this halt winters command effectively becomes a simple exponential smoothing model. Is it clear? All right. Now, similarly for this particular model, if you look at it, all right, this is what it is. You have the alpha, you have the beta, gamma is false. All right, this is the coefficient value. And we can do the prediction, how many values into the future. All right. And sorry. Yeah. When I do that, I have these prediction values. Interesting. 4020.46, 4020.46. Why are all the 4 predicted values the same? Why are all the 4 predicted values the same? Any idea? Obviously, these are the 4 y hat values corresponding to the 4 test y values. All right. So basically, we have 1 to 38 as the train, 39, 40, 41, 42 as the test. So this corresponds to 39. The predicted value corresponds to 39. This corresponds to 30, 40, 41, and 42. Why are they all the same? Why are all they the same? What is this model that we have built? Please tell me, what is this model that we have built? This model, what is the model? Please respond. Others, please respond. Think. 1 more minute. Okay, I'll give the answer. This model here is not halt winters, but it is simple exponential smoothing. Simple exponential smoothing. And what does simple exponential smoothing assume? There is only level. There is no trend or seasonality. So if you have a level, level is what? One single value. So therefore, the forecast will be that same value for everything. Is it clear, friends? Is it clear? Do you understand why I was waiting for you to, catch that point? Yeah? Do you understand? Yeah? That is the reason all these values are going to be the same. All right? Now, if you plot these predicted values, what is this? This is the model. All right, this is what the forecasts are. Okay, let us also do the MAP value. All right, so let me do the MAP and check the MAP. 16% error. Oh my God. I think our simple moving average was better with only 8% error. All right. Now next, using the same halt winters command, I'm going to run a double exponential smoothing model. Double exponential smoothing or Holt's method. All right. You can probably check this out here. Holt's method is also called double exponential smoothing. So I'm going to give the alpha beta. I'm going to give alpha and beta, but gamma I'm going to say false. So when I run this, I get alpha beta values. And then when I look at the predictions, and I actually look at the predictions, you see, obviously it is moving up. All right, it is steadily moving up. Why is it steadily moving up? Because it is the Halt's method or the double exponential smoothing. All right, and we can now plot it, and you will see a nice smooth slope, upward slope. All right, you will see a nice smooth upward slope, and then you have the MAP for this. Now let me also check the MAP while we are at it. Not bad. I think as good as the simple exponential smoothing. Now what I'm going to do is I'm going to run the Halt Winters model, the Halt Winters model, right? Alpha, beta, gamma, the default values that are provided to us. And when I run this is the alpha, beta, gamma. These are some coefficients not to be dwelled upon. Run it and then look at the predicted values. All right. 4820 4625 4318 5019. So what do you see here? By looking at this itself, we should be able to make out that there is an up down kind of a thing. If you plot it, you get the same thing, which is what you would expect. All right, which is what you would expect if you are taking into consideration the level, the trend, and the seasonality. All right. So this concludes as far as the testing of the models are concerned, but you must always remember that how we are basing the entire decision on some statistician's knowledge of it and saying 0.2. All right. You may want to do a trial and error for various combinations of 0.2, 0.15, 0.05, various combinations of those values. You may want to do a all right. So to take care of that, we are now going to build the Holt-Winters model. I mean the Holt-Winters command again. Again, I'm going to give alpha, beta, and gamma as false, but I'm silent about the alpha, meaning I expect my model to choose an appropriate alpha value. I expect my model to choose an appropriate alpha value, all right, and build the model. So when I run this and when I look at the output of the model, it has taken the alpha value 5.50200001 through some internal optimization calculation has done that. Now let me look at the prediction. Obviously the predictions have changed. Let me plot the prediction. It's going to be pretty much the same. The MAPE value, mean absolute percentage error, 9.09. Now remember, what was the MAPE value when the values were not optimized? What was the MAPE value when the alpha value taken was 0.2 and the default value 0.2 and not the optimized value of 0.50? It was close to 16 if you remember correctly. All right. So by choosing an appropriate optimized value, we have managed to improve the MAPE value, but the MAPE value is not all that great. In fact, the MAPE value, okay, what I did not show you was, let me show you now. Let me go up. This was the model where I had put alpha, beta, gamma. All right. Now, if you look at this MAPE value, does not exist. Maybe I did not execute it. 3.58. This is by far the lowest. All right, 3.58. Now here, next one, we are going to again use the same command Holt-Winters, but it is going to be only a Holt's model because we are saying gamma is equal to false, but alpha and beta you choose. So the model chooses and the model chooses 0.57 and 0.31 as the alpha and beta. All right. And then we convert it to a data frame and then we look at it. This is what it is. Again, it is steadily increasing. If you plot it, you can see it steadily increasing. Let me just increase this size here so that for future plots, it is going to be good. All right, steadily increasing. And then you can do the MAPE measurement and that value is going to be 8.6. Finally, I'm going to run the Holt-Winters command and run the Holt-Winters or simply the Winters model. All right, run the Minter's model, and when I execute this, when I execute this, what happened? Yeah, when I execute this, I get alpha, beta, and gamma. My God, 0.8, 0.89, 0.9 almost. The optimized value is what it is saying. All right, and then do the prediction. Look at the predicted values. It is starting and going down and then up. You plot it. This is what you get. And when you look at the RMSE, remember the corresponding RMSE for the alpha, beta, gamma default values 0.2, 0.15, and 0.05 were some 3.4 or something. All right, were 3.4 or something. And here the value is going to be 2.39, 2.4. So definitely a massive improvement when you let the optimizer choose the appropriate or the best alpha, beta, gamma values. All right. Okay. Now, what we can do is we have all these values available. Just create a data frame, a nice sweet data frame. All right. Put it into the data frame and have the first column have these values. Then if you look at that data frame DEF data frame map, this is what it looks like. The column headings are pretty absurd, very long column names. So what I'm going to do is I'm going to give column names like this. Now when you view it, it is pretty nice. All right. Now if you sort it based on the data, so we have halt winters N ABG alpha beta gamma, and says alpha beta gamma values are not given. All right, we have not given the alpha beta gamma values. That is the best model. The next best model is the halt winters where alpha beta gamma was given and the MAP value is 3.53, so on and so forth. Now, can you tell me why is the alpha beta gamma models better compared to the alpha or the alpha beta models? Any reason why they are better? Any reason why they are why they are better? All right. Let me explain why. Let me go back to the data. This is the data. And now please tell me, does this data, listen very carefully to my question, does this data not have seasonality? Yes or no? Is there no seasonality in this data? Is there no seasonality in this data? Please answer. You may want to answer slightly detailed. Yeah, everybody respond, please. See, there is seasonality in this data. That is why we have the up, down, right? Is there trend in this data? Do you see trend in this data? Very much. Trend is also there in this data. What about level? Is level there? Obviously, level will obviously be there. Then my question to you is, why did we do this? 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 Why did we build these models? Knowing pretty well, again the same thing. If we had spent, or if I was hoping somebody would point out when we started doing the simple exponential smoothing, nobody pointed out. I was hoping at least when I told you people about how simple exponential smoothing assumes only level and therefore all the four forecasted values are going to be the same, at least then I was hoping somebody would catch. Nobody caught it. Now do you understand, friends? Now do you understand? Right? That was the reason why I was asking you, why do we do that? Okay. Perfect. So you get the point. So you have to be, again, I'm reiterating, we have to be very, very careful with the EDA. Don't waste time in experimenting with all models when probably a limited model is more than good enough. Sorry. All right. So now we have built this. Now what we are going to do, we are going to use the Holt Winters model on the TS sales, the entire data. All right. And the new model gives me the value 0.3, 0.2, 0.99. And then I can plot this. All right. I can plot this. And this is what the model looks like. All right. Forecasted model. And then I can do the forecast for the horizon, that is beyond 42. Till now we were having till where is that? Till now we were having till 38, right? 39, 40, 41, 42 we were doing. Now we are going beyond 42. So 43, 44, 45, 46, these are the values. Obviously, we cannot test them for accuracy because they are actually the future values. Are we good? Is it clear? Perfect. Now, thankfully, we have multiple ways of doing the same thing. Now, what we have done here, we have used Holt Winters. Now, there is another package, and with that package, we have an option of doing the same thing using what is known as simple exponential smoothing. So, when we do simple exponential smoothing, we do only simple exponential smoothing, nothing else. All right. So, we have to give the alpha value. All right. No beta, no gamma, because it is actually simple exponential smoothing. The behind the scenes formula, the logic is exactly the same with a slight variant. That is why the predicted values and the accuracies will be slightly different. So I build the model. This is the model outcome. These are the forecasts that it gives me. All right, default forecast. Then I'm going to plot I'm going to do the forecast for the horizon is equal to H, that is 39, 40, 41, 42. Figure margins too large. Yeah, do it again. Okay, and then when I plot it, this is how the plot looks like, and then I can do the map, and this is what the map looks like. 16.12, pretty much comparable to the same map that we had gone there. Now next we are using the command Holt. Holt requires two inputs, alpha and beta. So alpha and beta values are given. I have given 0.1 here. You may change it to 0.15 as the case may be. This is the output of the model. And we have the forecast for the future. All right, the horizon. And when I execute that, I get the values. And because it is, oops, all right, you can see that the values are going up, down, up, down. Sorry. This is Halt's method, right? Not the Halt winters. So it is going to be only going up because there is level and there is trend. There is no seasonality. So no down, only up or down. You can have a downward trend also. All right. So you plot it, nice smooth movement upwards. Look at the MAP and then you have the MAP value also. This is 0.8. Next, the alpha, beta, gamma, 0.1. We do that and then look at the output, do the prediction. And these are the values. You can see it is up and down is both there. When we plot it, you can see the same thing. And the MAP value is nice and sweet, 4.4. Here also you can do the optimization. You have to specifically mention this particular SES requires alpha, and I say alpha is equal to null. All right. So we look at the summary. This is what it is. Then you can probably run this on the data frame and you do the prediction. These are the predicted values. You can plot it. Again, pretty much the same thing. The RMSE, the MAP is what I'm more interested in, which is from 16.9. This is again something similar to what we have done when we did the 0.2, the alpha is equal to 0.2 and when we did this particular value. All right. Now something similar, we are going to do the alpha here. All right. And then prediction, look at the prediction, up and down, and moving up, my bad. This is alpha, beta, right? My bad. Halt. So all moving up with optimized values. Finally, we do this with the optimized values. And again, we create a data frame. All right. And when you view the data frame and you sort it, once again, you will have the Halt winter alpha, beta, gamma, MAP new with the optimized value. All right. Halt winter N means the values were not provided. And we have this. Now we want to do the final model. So we are going to take TS sales, the complete data up to 42 values. Alpha is equal to null, beta is equal to null, gamma is equal to null. That is, you yourself figure out what is the best value. And you do the plot of the forecast, do the forecast new, and you have the forecast. Now I was a little fast, I agree, in the second part of it because I was only running the same command. Rather, I should say I was only running the same functions using a different command, right? So basically, that is why I didn't want to, take the same speed. Is it clear, friends? Is it clear? All right. So, yeah, any questions till this point of time? Because I'll be stopping a little early today. There's a reason for that. One is I can definitely take for another 10-12 minutes, but we are on the weekend. All right. So whatever I'm going to take for the new topic for about 10-12 minutes, it is definitely you're going to forget it by Monday. All right. So obviously then I have to do a recap. Also, I have certain commitments right now. Some personal issues have been called out. So for that reason, I'll humbly excuse myself. I'll apologize to you people. So if you have any questions, I don't mind staying back and addressing them. Are you guys okay to leave me 12 minutes early, 10 minutes early? No problem. Yeah, any questions? Any questions? Yeah, stop live, please. Team, stop live, please.